Okay, this week we're learning about bird sounds and vocalizations and the study of bird sounds and how we use and understand bird sounds. Before we get started focusing just specifically on birds, it's important to understand a little bit about the physics of sound. So all really sound is waves of air molecules traveling. And there are different elements to those waves that can make a sound have a different quality to it. And so to make sound, you need some structure to make the sound, to change a pressure gradient in the air molecules. And you also need a sensory organ, the ear, to receive those sounds. And so when a sound is made, if you think about the humans, we make sounds with our larynx, with our voice box. Birds have a very similar structure. It's actually slightly different and gives them a little more variability in what they can do with the sounds they make, called the syrinx. And so our larynx, when we're making a sound, we have air traveling in and out of our lungs as we breathe, and we can constrict, using muscles, we can constrict our larynx to different degrees to make sounds that are of different pitch. Okay, if you constrict your larynx to be very tight, you can make really high sounds, and if you relax it to be very open, you can make low sounds. And then the amount of air that you're pushing across the larynx influences how loud the sounds are, and the same is true with birds. And so all sounds really are these waves of air molecules. And so when that sound is made, it travels out from the organ that's made it, and then to hear a sound, you need a sensory organ that receives those vibrations. And so we're not going to really talk too much about the anatomy of the ear, but the ear in humans consists of three parts: the eardrum, and then the bones, and then the inner ear. And basically, they basically transfer the air, the molecules, the waves of air molecules in the air into vibrations that are received and processed in the brain. And so here is a visualization of a bird making a sound, and you can actually look at this pressure wave moving through the environment and being received by an ear. Here's the bird. Oops, I'm going to play this again. Here's the bird. It's making a sound. There's that sound wave, that area of high air pressure, that sound wave being received by an ear. So that's all sound is waves of pressure. And the reason that visualization is showing what appears to be the sound get larger and larger is sound tends to travel out in waves, much like when you throw a rock in a pond and you see those waves of water travel out in a circular motion. And so when we are measuring sound, there are two major ways that the sound can vary. And this, what we're looking at right here, is called the waveform view of a sound. And along the x-axis, we have time, okay? And then here, in this case, the y-axis of a waveform view is amplitude. So it's that change in pressure from high pressure to low pressure. And so it's this peak and trough, the distance between the peak of the wave and the trough of the wave. So the peak of the wave here is that point of high pressure. The trough is the point of low pressure. And so you can measure how loud a sound is by looking at the difference between the peak and the trough. The larger the difference between the peak and the trough, the louder the sound. The smaller the difference between that peak and trough, the quieter the sound. And so that's one way you can understand one element of sound that we detect with our ears. You can also, by looking at a waveform view, though it's not quite as easy as some other views, you can also say something about how high or low pitched that sound is. And that is by measuring the distance between two peaks of a wave. Here's a nice explanation or a diagram that's describing this high air pressure, normal air pressure, and low air pressure. And that's looking at that amplitude of the sound wave. And then when you measure the distance between two peaks of a wave, what you're looking at is what they call the wave cycle. So how fast it takes to hit two high pressure peaks in a wave, is that duration. And that influences how high-pitched or how low-pitched a sound is. Waves that are very tightly clustered together so that there's a very short time period between two peaks are high-frequency sounds, okay? And high-frequency sounds are also high-pitched sounds. When you have sound waves where the peaks are very distantly spaced apart, those are low-frequency sounds. And there's different abilities of those sounds to travel through an environment. High-frequency sounds are usually really good for being able to find a location, okay? And so high-frequency sounds are often very good at providing the location information for something. And if you think about bats and their use of echolocation, they're using high-frequency sounds to locate objects. Low-frequency sounds actually travel long distances. And so animals like whales and elephants actually can communicate over long distances through these low-frequency sounds. But what that would look like would be differences in these distances between the frequency peaks. Another way that we view sounds is using a spectrogram. So spectrogram view is really focusing on looking at changes. It's a visualization that shows you much more readily the changes in the frequency of a sound, so the changes in the pitch. And so what we're looking at right here is time again on the x-axis and frequency on the y-axis, okay? Here would be a sound that is of constant pitch, okay? Constant sort of mid-frequency pitch on this scale over time. And so putting this together, if you were to see a waveform of a sound or of several sounds lined up next to each other, you should be able to, or you could, if you looked hard, if you looked at these sounds and remembered these elements of both the amplitude and the duration of these wavelengths, you should be able to have some idea of how the sounds might compare to one another in terms of how loud they are and how high or low pitched they are. So in this upper diagram, what we have is a sound that is of the same pitch. Okay, so both of these sounds, this sound here and this sound here, they're the same pitch. When you measure the distance between the peaks of each one of these waves, it's the same as the distance between the peaks of these waves. So the pitch, the frequency is the same, but this sound is quieter than this sound because what's happening here is the amplitude is changing. The distance from the peak to the trough is much larger in this louder sound than it is in this quieter sound. On this bottom image, what we're looking at is a change in frequency, but no change in volume. Okay, so again, if you were to take a measuring tool and measure the distance between the peak and the trough of this sound, it would be the same as the distance between the peak and the trough of that sound, meaning the sounds are the same volume. However, when you measure the distance from peak to peak, what you find is this first sound has a lower pitch, is a lower frequency. The distance between the peaks is larger. And then this sound is a higher pitched sound. The distance between these peaks is much smaller. And so what we're seeing here are two sounds that are of the same volume, but they're different pitches. What these same sounds would look like in a spectrogram view would be quieter sound and louder sound here. Now, if you were looking at something like and the way that's indicated, I guess I should mention this, in a spectrogram view is usually either a color gradient, or if these spectrograms are in a grayscale, you would find differences in the shades of gray in the actual sounds. And so here the color scale is going from something that's like blue up to something that's close to yellow or white. And so the only way that we can tell that these two sounds are a different volume is just because they have a different color to them, okay? And you'd have to know what that scale is to know which one is the quieter sound and which one is the louder sound, because we see no information visually other than the color in these two sounds. It's because they're happening at the same pitch. This lower spectrogram you can see this difference in pitch here, and you can see by looking at the color of the two sounds that they actually are the same volume. They have the same color value, and so they're the same volume. And so when we look at spectrograms, what we are really able to focus on is the changes in frequency, which can be really important in understanding birdsong. So here is an example of an actual birdsong, and this is showing us that song in waveform view, where we're looking at shifts in amplitude, and we can also see that song here in spectrogram view. And so we can see that this looks to me like one note that's a little bit higher than the other note. And to me, this second note looks almost like it has a little change in frequency from low to high. So let's play it and listen to it. Oh, and also I'll point out that here they're giving us that scale of volume here from quiet to loud. Okay. And what I can see in this sound is somewhere around the middle of these notes, you have them being at their loudest. And in this second sound, the second part of the sound is a bit louder than the first. So I want you to take just a minute and think, what does this sound like? We may not know the pitch just yet because it's not showing it to us, but think of, by looking at those lines, what it might sound like. Okay. I'll also point out before I play it that you can actually look at this shading here and compare it to the waveform to see the shifts in volume. So I'm going to play this song now. Okay, that is a black-capped chickadee, a typical song, which a lot of people describe as sounding like, "Hey, sweetie." So I'll play again. Okay, so you can actually track it. I'll play it one more time, looking at those shifts in volume and pitch here. Okay, so start to think about that. When we're looking at units, if you're looking at a image of a sound in waveform, the units can vary, but they tend to be decibels. Okay, so decibels is a measure of volume. And when you're looking in spectrogram view, it's hertz or kilohertz are your y-axis values. And that has to do with the numbers of cycles per unit time. Okay, so here is a series of sounds by a black-capped chickadee. Since we heard that song before, we can look at some of the other types of sounds. And in another video, I will go over vocal repertoires and the different kinds of sounds birds can make. But in the case of chickadees, the chickadees make lots of different kinds of sounds. They have contact calls. Okay, and a lot of these higher pitch notes, you can see these are just in spectrogram view because we can see these differences much easier in a spectrogram view than we could see in a waveform. So a lot of these little peak, 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 peak notes, and then going down to a buzzy kind of chicky sound. Okay, this is an alarm call, and I can look at it and see, oh, these elements here look kind of similar to these elements here. They're lower pitched though, and they have these what we call harmonics. And so we're looking at here, when we're looking at these bands of sounds that seem to be parallel to one another, these are the harmonics of the sound. And when you see a sound that has lots of harmonics, it tends to sound kind of buzzy. So let's listen to that. Okay, sound pretty similar. But there are some differences. And that D note, it has been found, indicates something about danger. And the chickadees tend to make more of those ending D note sounds when the danger seems to be a greater risk. Comparing those sounds to the song of the chickadee, it's interesting because you can see, for one thing, the song is a simpler type of vocalization in chickadees, which is the opposite of what we find in most birds. And also, you may see that there are no harmonics in this sound, okay, which means in terms of how the ear perceives it, It tends to be a more pure tone. It doesn't have that buzziness to it. So let's listen to it. So there's that same, hey, sweetie, sound there. And you can see the three notes, a high note, a low note, and a mid note with some shifts in volume, with the lower note being the quietest one. Play them all through one more time. So birds also, songbirds at least, birds that learn their songs. Some birds are born with their songs and some birds learn their songs, and we'll talk about that in another video in more detail. But you can actually visualize birds that are less experienced and are learning their songs compared to birds that have already learned their songs. And this is a white-throated sparrow. This is a type of bird that learns its songs. And the process of song learning in birds is very similar to the process of acquiring speech in humans. They go through different phases where they're learning the sounds. And young birds during the plastic song phase are engaging in sounds that are somewhat equivalent to the babbling of babies, the babbling and the early speech patterns of young children. And so this is what that plastic song looks like in spectrogram view compared to a crystallized song. And I can see a lot more buzziness. The song has more variability in its volume, but there are some elements that are similar in that there's some high notes here at the beginning, just like here, and then there's some patterns of notes following, but it's more variable. So let's listen to a plastic song of a young white-throated sparrow. Okay, and then this is its crystallized song. Okay, and so the notes are, the hitting of the notes are much less certain in that plastic song. It's almost like somebody practicing a song, trying to get the pitches correct. And you can see this all in these spectrogram views. So I'm going to pull up an actual spectrogram of a song so you can look at it just get another example. Waveform and spectrogram views in the program Audacity that I've mentioned in a previous video will be really useful for visualizing your own songs. But it's nice in Raven because we can line them up, the waveform view, which is on the top, and the spectrogram view, which is on the bottom, so that you can actually see them both together and you can play them together and see the changes. And so this is the song of a canyon wren. And I can see quite readily in the waveform view that this song goes from quiet to quite loud and then starts to get quiet again, with some notes kind of wavering between quiet and loud at the end. I can't easily see, looking at the waveform view, the change in pitch that's happening. I can only see a change in volume. But if I look down at the spectrogram view, I can actually see these changes in pitch, and I can also see the volume. So I can see where it's red here is where you have your loudest volume. And so you can actually see the thicker red bands here in the middle that correspond with these larger amplitudes of the sounds. And then the units that Raven uses for amplitude are a little bit different than the decibels that you tend to see. But here we're seeing this scale, and it's in what we call kilohertz. So kilohertz is 1,000 hertz. Let's listen to this canyon wren song. Okay, so this is something else that I can see that we're hearing. I'm going to play it one more time. And what I can see is in both of these, we see that I hear the quiet to loud to quiet. I see the decrease. I see going from high pitch to low pitch here. But there is also something we're seeing here, is that these are notes that are repeated in their pattern. So they're kind of these little squiggly notes, and they tend to stretch out as the song continues. And what that sounds like is the song slowing down. And the slow down pattern is not so much in the spaces between the sounds, but the sounds themselves get longer and longer and longer. So let's play it one more time. Okay, and in some players, like in this one, turn the volume down just a little bit. I don't know if it's going to be so loud for you, but that was kind of loud for me. You can change the play rate. I'm going to just change it to 2.0 and see what that sounds like. If you're really not feeling you're getting all that information and hearing everything that you're seeing, you can slow down how fast the song plays back. Oh, that's speeding it up, sorry. Let me change it to 0.5. So you can follow along much more readily sometimes when you slow songs down. Birds can make really intricate, very rapid notes in their songs that can be hard for an ear to detect. I'm just going to slow it down one more step so we can just hear it that much slower. Okay. And so hopefully you've gotten a good idea of what kind of information is available in these different views of a sound. And a good purpose for this is as you're going through doing your field methods for this week and last week, you're making recordings of bird sounds. And if you start to visualize them in programs like Audacity, you can start to understand them a lot better. And you can actually start to look at these patterns and recognize visually the songs. And so if you're more of a visual learner, it will help you with learning birding by ear. All right.